time we discussed matrices in general, and today we're going to discuss the idea of matrices, but from a simpler perspective. And with simpler perspective, what we mean that we're going to spend some time dealing with vectors. The vectors are, you can consider vectors as the columns of a matrix. Okay, so they are just constituents of these small sections of the mathematical construct which is considered a matrix. And the basis of the understanding of vectors, we're going to use it a lot during the semester, including when we talk about the relevant spaces which can be related to the matrix. A matrix, it has a domain, it has a range, it has several spaces associated with it. And in order to understand all of these, understanding the vectors is very essential. So let's continue. And the first thing that we want to say or to discuss is the following. Let's assume for a moment that we have a Cartesian coordinate system that looks like this. And we identify, let's say, a vector which is 2, 1. This is here 2, 1. And this 2, 1, here we have it. This is 2, 1, this is x, and this is y. This is 1. And then another vector is, for example, 1 minus 1. 1 minus 1. So here we have another vector. So let's call this one T1 is equal to 2, 1. T2 is equal to 1 minus 1. And these are both vectors, okay? And now what we can define is that we can define a union of points that can be written as such. Assume for a moment that we have CT1, where C is an element of R, which means the C is a real number, which can be a positive, negative number. It doesn't have to be integer. And and this C, since it can be an element of R, imagine for a moment a list of C being 0, 1/3, 1/4, half, 1, 2, and so on. So let's see. When C is equal to 0, what point do we get?
The origin.
Exactly, thank you. This is the origin. When C is equal to, let's say, 1, I guess we get this point. Okay. So with this example, we understand that with T1, we're defining a pair of numbers which define a point in the two-dimensional Cartesian coordinate system. With Cartesian coordinate system, we have x and y, which are the two bases that have conjugate directions or perpendicular directions or orthogonal directions. So we said that this point, we can assign when, so we did this and this, when C is a half, so let's say C is equal to 1/2. This means that CT1 is equal to 1, 0.5, right? And this 1, 0.5, it's a point which is going to be somewhere here, okay? And then we can select when C is equal to 2, CT1 is equal to 4, 2, right? So here we get 4, 2. This is 1, 2, 3, 4. 2 is the other coordinate. So we get this point. So as we can see, we are generating a series of points. Now, what is the union of CT1? So union, do të çfarë është bashkësi që mbledh të gjithë pikat, të cilat përshkruhen nga kjo shkruajtja këtu. So what is the union of all of these points? What can they constitute together? And C can even be -1. Imagine for a moment, if C is equal to -1, we get here -2, 1, 2, minus 2, minus 1, we get this other point. And we get also this, we get this, and so on. So what could all this point constitute?
The T1
Is what?
the T1
A line.
block.
It's a line. Okay, that's correct. So we get a line if we just add up all of these points together, or we consider all of those on the board. Now, with all of that's one example. Now imagine for a moment that we have two vectors. We have T1 and T2. What is the union of C1 T1 plus C2 T2? What is the union of all of these points? Now let's check. Let's assign C1, C2. Let's say C1, C2. I'm going to erase this one very fast. I mean, once we are done with this, also C1, C2, let it be 1, 0. Okay. Then let it be 0, 1. Then let them be minus 1, 0. Then it can be 1, 1. Okay. Or it can be 0.5, 0.5. Let's see where these points are. Now, when C1 is 1, 0, what do we get here? We get, actually, to lead the I, let me write here C1 times 2, 1. Let's not forget, we already did this here, plus C2 times 1 minus 1. Okay? And let's see, what did we say? We said C1 is 1, which makes this 2, 1. So the first point is this cross. Okay, let's make this with crosses. Or maybe we can make circles. Open circles open circles are better. So we had this point before. Now we make an open circle. Then we make this 0, 1. If this is 0, we do 0 times this plus 1, 1 minus 1, and we get this other point. So we did this, we did this. What is the point which is denoted minus 1, 0? Let's do this. Minus 1, 0. This is equal to minus 2, 1 plus 0, 1 minus 1. This is minus 2, 1. Where is minus 2, 1? Minus 2, 1. No, is it correct? Or did we make any mistake? This is minus 2, minus 1. Sorry. Because the minus multiplies also the 1. Minus 2, minus 1, it looks like we get this point here. And let's see when we have, what other important point we have? We have 1, 1. When this is 1, 1, we're going to get here, let's change here 1, 1. The answer, this is going to be 3, 0. Okay? So we have this together. Where is the 3, 0? 3, 0. It's this point, and then, so we did this. Let's check when it is 0.5 and 0.5. Here, this is 1 over 2, plus 1 over 2, and what should we get then? This is 1.5, and this is 0, 0. Okay, 1.5 and 0. 1.5 is somewhere here, 0. So as we see, we find a lot of points all around the board. But now, with these solutions that we are providing on the board, what do you think? What could be the union of C1, T1 plus C2, T2? The first one, it was a line. Now, with combinations of these two vectors, I guess we can define any point which would be across the board. If you try hard, you can always find C1 and C2 such that if you want to go to this point, you can combine these two given vectors which are shown on the board, which is this but we draw this in double line and this.
Two zero.
These points, in fact, is going to define a plane. Okay, so if we combine, if we have a random combination or linear combination of two basis vectors, which in this case would be these two ones, we can define a plane. And with this plane, this means that we can define, for example, the whiteboard. So this whiteboard that we have here, we can scan all the points using these two vectors. And the keywords, we can say that T1 and T2, they span the plane. Or let's write here two-dimensional plane. Two-dimensional plane, which in this case, the whiteboard is a two-dimensional plane and it can be spanned by these two vectors. This is the keyword, okay? Now, imagine for a moment what is the union. This is another question for you of C1, T1. And to answer this question, we're going to pick someone from the class according to the alphabet. We have Aidina. So Aidina, if after Aidina we have Alan Petro. So Aidina, what is the union of C1, T1 plus C2, T3? Where T3 is equal to 4, 2. What do you think here? So, Edina, can you give an answer for this?
The microphone doesn't work. You wrote it.
Okay, is it better?
No, not yours. Her microphone.
Okay. Let's see. I have a couple of comments. My mic. Okay, since the beginning. Okay, after Edina. Okay, now I see the comment. Then I can have Alan.
6 and 3.
Let's see, 6 and 3. But okay, so this is 6 and 3. Only. Let's write this one. This is 6, 3, but this is when C1 is equal
1
to
and T1 union.
is equal to 1, okay? So you are saying 6, 3 only when these constants are both equal to 1, but they can also change, they can have different combinations. In this case, this is it. But my question is this, that's true. What is the union of all possible points of the linear combination of these two vectors? 2, 1 and 4, 2. Actually, let's do it. 6, 3. Where is 6, 3? 6, 3, it's 1, 2, 3, 4, 5, 6. It's going to be somewhere here. Okay? I'll try to do a rough drawing. And 3 is 1, 2, 3. So more or less, this is going to intersect somewhere here. Okay? This is the point 6, 3. And probably this looks like it's close to here.
It's a line.
The union is going to be a line.
Line.
Is this a line?
Yeah.
I think it's a plane.
Okay.
Yes.
Okay, we have to think between A option, it could be a line, B, it could be a plane. So who thinks it can be a line? Can you enter this in the comment section? I want to see you press 1, okay? You press 1 if you think it's going to be a line. Okay, I'm counting. And the line is 1, and plane is going to be 2. If you think it's a plane, enter 2. Okay. We have a few more from you to enter your answers. Okay. We have quite a few ones, So we have quite a few possible answers or votes for being a line. In fact, let's pick another combination. Let's change. You can do it like this. You can set here 1 times 2, 1 plus 0 times 4, 2. So if this is the case, what do we get? I think we get 2, 1. So we get on top of the previous vector. And the answer for this one is going to be a line, okay? Because this new vector, the 4, 2, it is equal to, we have here the t3 is equal to 2t1, okay? So just by changing this parameter, so actually we can write it like this. C1 plus C2, we can write this one C1 times 2, 1 plus C2 times 2 times 2, 1, right? Would you agree that this is the same thing? We just expressed the second vector T3 like this. And this would be equal to C1 plus 2C2, which are still constants, times 2, 1. We're fine, right? So this is still true. Now, the constant C1 and C2, they are random numbers. And this was also a random number. So since we can write it like this means that all the points are still, all of them, they can be still described by this vector 2, 1, okay? Because T3 is equal to 2T1, which means that the T3, if we give the T3 here, it is redundant. Or useless. We don't need it. The information provided by T3, which is twice of T1, it can be covered by this. So the correct answer here is that the union between here C1, T1 and T2, it's a plane, and here, maybe I can erase this. Now this is a line. So here on the board, we have the union of C1, T1 is a line, union of C1 and, T1 and T2, it's a plane, union of these is again a line, okay, and if we understand what we have done so far, this provides, this means that we have understood a little bit how we can describe planes and the lines. Now, imagine for a moment that we have 3 vectors, let's write them here. And by the way, these vectors that we are dealing so far, they define a point using a pair of numbers. So in this case, we can simply state that T1, T2, and T3, they all are members of R3. Sorry, R2. Why? Because these points are defined by a pair of numbers. It's as simple as that. Now, we can also define, well, let me think, no, before I jump to the new argument, let me ask you another question. So, what will be the union of, actually, when you say the best word is to say union of C1, or let's keep the same terminology. Let me write it like this. And by the way, I made a mess here. C1 T1 plus C2 T2 plus C3 T3. These are 3 vectors here. So what is the union of all of these 3 vectors? What do you think?
A plane?
I think 3D.
3, okay, we have also, it's a possibility of being 3D because we have 3 vectors, which means that a line, it is 1D, a plane is 2D, and if we have 3 vectors, the first possible candidate is to have a structure or something like a volume or a 3D region. So, the question here is it going to be a 2D or 3D? which means that this is maybe the whole space. This would be a plane. These are the question, or 3D. Now, I want you to carefully, I want to get the opinion of the next in line after, I don't know, Alan, did Alan answer?
Yes, I was the one that answered.
Alda Kata? What do you think, Alda?
I also think it's a 3D, but I don't know.
You think it's a 3D. Now, but Alda, did you follow this argument that the union of C1 and T3, this was a line, okay? So we had two vectors, but in fact, it was not two, it was one, because we had one vector which was pointing like this, and we had another vector which was twice of this vector, okay? So these two vectors and this, they can tell the same thing. They don't offer any new information, because here I have this vector. This is the preserving the direction, this is twice. But to represent the endpoint of these two vectors, I can do it with this one also, right? Just by multiplying by 2. So here, Alta, you are suggesting that it would be 3D, but if you come back to this argument, we agreed that this was a line because T3, it was linearly dependent on T1, okay? So we could even take this away and we would lose nothing. Also here, similarly, since T3, it depends on T1, in fact, this means that we can forget this completely and consider only C1 and C2, then this would be a plane. So the correct answer here is a plane. Is it clear, Anna?
Yes.
Okay. So this is, we are still dealing, we have three vectors, which are elements of R square, and it looks like they can span a two-dimensional space, two-dimensional space. Now let's imagine three vectors, which is V1 is equal to 1, 0, minus 1. Another vector is going to be V2 is equal to 2, 1, 0. And V3 is equal to 1, 1, 1. Okay? So what could be the union of these three vectors? Which means that what is C1 V1 plus C2 V2 plus C3 V3? How would Alisa answer this?
Don't really know.
Sorry, Alisa, you said you don't know?
No.
Okay, so here, these vectors, if we want to show these, how they look like, we need a three-dimensional space, first of all, which means that we have here x, y, and z. So here for x, we have x here, it's 1, okay? The y is equal to 0, and the z is minus 1. So if we are here, from the z, we come down 1 unit, and then the resultant vector is going to be some point down here, okay? Maybe you can do a better job if you draw this. V2 is 2, 1, 0. V2 is 2 unit here, 2, 1, 0, which means that we will remain somewhere on this xy plane. So in fact, actually, if you look at this one, when z is 0, that means that you are staying on the xy plane. Let me write this like this, xy plane. This one, it is xz plane. We are trying, for a moment actually, we never forget that we are working with matrices. But for a moment, we are trying to extract the geometric understanding or geometric meaning of these matrices when they are vectors, okay? So it's not that we are moving out of our topics, So this vector, it's on xz, this is on xy, this is on xyz, okay? So then this is going to be somewhere here, again, really, it's a little tough to draw the 3D on a 2D board, and maybe I need to do a better job, but all of these three vectors, a suggestion, Alisa, I think this is I was answering. I was asking the combination of these three vectors, it is rather going to be a three-dimensional space. Actually, any point in your room that you are sitting right now, listening to the class of linear algebra, any point in your room, you can describe by these three vectors. So you select the corner of your room, which is on the floor, two edges on the floor, is going to be x and y, and one third edge, which is going to be along the z. You can define these three vectors in your room, and then for sure, using these vectors, you can go to any point in your room. So you can go to the ceiling, you can go to the lampshade, to your books, which means that they can span a three-dimensional space, because V1, V2, and V3, we can write it here, or here, or even V1 is enough to say this, is a subset of R3, okay? Because each point, it is represented by a triplet, okay? So we have a triplet of numbers. So this is what we get so far from the vector analysis. Then we can ask another further question, which could be the spanning of V1, V2, V3, and I can add another V4 here. V4 can be 3, 1, minus 1. And the question, I can use this part of the board, because I think they were clear so far. What is the linear combination of C1 V1 plus C2 V2 plus C4 V4? This is the question, and for this I want to ask Andy. Andy, what do you think? Sorry, this is V2. What is this space that can be defined by the points that
Plane.
It's a plane. Why is it a plane?
Because C4, V4 is the sum of the former vectors.
That's correct. Okay, that's done. So here we have a plane. We do have three vectors. That's true, but this is going to be a plane because this is a function of V1 and V2. Because if you add, this is actually equal to the sum of the first two. So this means that this one is telling to us nothing new. The information that this can provide is we can do it with this. It's enough. Okay. So this is really a plane. That's good. What about this then? What is C1 V1 plus, let's say, C4 V4? For this, let me ask Ardrisa. Ardrisa, so what is this? What is the union of points that can be described by V1 and V4, which are on the board? I have to scroll down, maybe we have some comments down here. No. So, Ardrisa, can you answer this? After Ardrisa, then we move to Ariola. Ariola, what do you think?
I think it's a plane.
Okay, that's fair enough. It's a plane because what's the name? It's a plane because we have two vectors. That's correct. And it's true that they both have triplets of numbers to be defined each of these vectors, but there are two, which means that we just have two lines pointing somewhere in space. So you can assume that you have a plane which can be oriented at different angles defined by these two vectors, because we know that any two vectors, they are going to look like this. Okay, I could use a board, but this is also effective. So these two vectors, whichever way they are oriented, they are covering this. They cannot do any more. Okay, so these were the vectors. Now let's come back or let's do this. We don't need to, how can I say, to define addition from beginning, because we know how addition is defined. But let's do just a small exercise. What is V1 minus V4? So how we add vectors? That's the question that we are talking. And for this, let's Armando. What do you think, Armando? What is V1 minus V4? Armando, I have a very good friend. His name is Armando, so I'd like to.
-2.
Armando? No, I want Armando Caray to answer this. Armando, can you please open the microphone? Answer the phone. Okay. Then we move to Benjamin. Benjamin, would you agree with what we're doing on the board? Or correct? Is this correct? Okay. Opinion left the meeting. Okay. So if we know how the vectors we do. This is just an exercise. V1 minus V4 would be the result shown on the board. If there is any mistake, please correct me. But I just wanted to, let's assume that we have another vector, which is T4, which is equal to 3, 1. Okay. And now let's think for a moment, what is T1 plus T2 plus T4? Okay, let's imagine that we have these three vectors. How do we add them? The way to add vectors, we do it, for example, we can have a vector like this, another vector here, and another vector here. If we want to add all of these, all we do is that we bring, so this is the end of a vector. Okay, this is called the end, fundi vector. This is the tip of the vector, Maya vector. We bring
The triangle rule?
yes, we can call it like that. Sometimes they call it the, yeah, you could say that. But you can assume the following. You just bring this vector, the second one, you bring this down here. So you join the end of the second vector with the tip of the first one. Okay, then you bring this third vector, you bring it down, you bring it like this, okay? This is the tip. So this is how we add vectors, okay? So fundin e vektorit të dy, bashkojmë majën e vektorit të parë dhe kështu me radhë, me vendosim njëri pas tjetrit. So for example here, we are asked to find T1 plus T2 plus T4. What is T1? T1 is T1, okay? So let's draw this again. T1 is right here. Then what is T2? T2 is 1 minus 1. 1 minus 1 is this vector, which means that we carry on this vector, we bring it right here. Okay, this is T1, this is T2. Then we have to add also T4. T4 is 3, 1. 3, 1 is this vector here, okay, which is shown here. This is T4. And now we have to carry this T4 here, we have to carry parallel and bring it we have to bring this end of this vector to here. So this means that this is 3, 4, 5, and 6. So this will come somewhere in here. So this is T4. If this is T4, this means that the answer is going to be from this point to this point. And it looks like what is the coordinate of this point here, based on what we have drawn on the board, it looks like it's going to be something like 6, 1. Okay? we try to do the best. When we draw this, it looks like 6, 1. In fact, if we add T1, T2, and T4, which is this, and this, let's see if that is true. We have here 3 plus 2, 5. It's true, right?
Yes.
Okay, it is true. Good. So this is also how we do the addition of the vectors. The same way we can define also the subtraction, because subtraction is just that one of the vectors is multiplied by -1, and we carry on the what's the name? The addition after we multiply by -1. Another important operation that we can do with vectors is the inner product. Okay, inner product. It is equivalent to the multiplication between two vectors. We call this one also dot product. Okay, dot product or scalar product. Or scalar product. Now, all of these, scalar is a matrix with dimension 1 by 1. Okay, a single number is just one row, one column. So if we have number 5, 5 is a matrix. So for example, 5 is a matrix, but it sounds like this, 1 by 1. Okay, this much it is almost obvious. But let's see actually, if we are talking about the product of vectors, how do vectors or matrices multiply? Can we multiply T1 times T2? What do you think?
No, we can't.
Why? Because this would be the multiplication of T1, it's a matrix which is 2 by 1. We multiply this with another matrix which is T2 is 2 by 1 also, right? Multiplication of these two vectors, it is not defined because these indices, they are not equal to each other. So we say that this is not defined. That's true, we cannot. But how can we multiply two vectors? We have to take the transpose of one of them. Okay? So for example, T1 is equal to, according to what we have on the board, T1 is 3, 1. So T1 is 3, 1, but T1 transpose, this is a vector, this is also a vector. What is T1 transpose? This is the T1 transpose, okay? So the column becomes a row. Now, the inner product, which is a product between any two vectors, it is defined as follows. So we write this T1 with T2. This is the inner product. This is how we denote it. This is going to be equal to T1 transpose times T2. Now, is this product defined now? This is defined because T1 transpose, it is 3, 1, which is 1 by 2. We multiply this with the T2, which is 1 minus 1. 1 minus 1, it has dimensions of 2 by 1. And what should be the size of the matrix if we multiply these two numbers?
1 times 1.
1, 1.
That's correct. Okay. We get the number here, which should be 1 times 1, because we have to read this from here. And if we ask here Daniela T.I., what should be the answer here, Daniela? Daniel, so if not Daniel, yes, Daniel, your microphone is active. Yes?
3 times 1 plus...
Yeah, we follow like this, right? So we multiply this whole row, we multiply with this column.
It's 2.
Okay, that's true, we get that 2. Okay, so here we are, 2. So this is the inner product of these two vectors. We have also what's the name? we can define also the inner product of a vector with itself. So we can also define the inner product of T1 with T1, and in this case, this would be equal to 3, 1 times 3, 1. And in this case, this would be equal to 10. Now, we are still talking about the inner product. After the inner product, we can also define magnitude of a vector. So T1, we can write it like this. How do you translate magnitude in Albanian? Datione, do you know? I mean, have you ever thought about it?
I'm not good at English.
There, value.
Length.
Is the length. So in physics, you're going to cover vectors. And of course, for sure, you're going to start with vectors. So when you discuss, we say that a vector, it has magnitude and direction. The magnitude is the length, është madhësia. Pra në shqip kështu përkthetje, pa ke parasysh që kur themi magnituda e tërmetit, se po përjapim fjalë, po zgjedhim shembull më të qitmushëm, duke përmendur. Or magnitude, this means madhësia or the length. So you have a small magnitude, that means that you have a very short vector. So this is defined as the magnitude of T1. This is the magnitude, and this is defined as the square root of the inner product of T1 with itself. Okay? So in this case, what would you say that the magnitude of T1 is, Dorina Deca?
It would be the square root of 10?
That's true. Yeah, exactly. It's going to be square root of 10 because this is what we see from the numbers that we have on the board. So this would mean this is going to be equal to square root of 10. Now we can. This is the inner product, the magnitude, so it looks at the magnitude is equal to square root of 10. And now we want to put forward another argument. We're going also, so you can take notes here, okay? So we said inner product, I'm erasing it, I'm taking it away. We talked about the magnitude. And now let's talk about something else, which is the following. So let's assume that we have here the vectors 3, 1. This is 1, 2, 3, 1. Here we are. And we have the vector, let's pick up 1 minus 1, T2, 1 minus 1. It is this vector here. I wish I had drawn this a little larger, but I hope it's also clear to you. And let's pick up another vector, minus 2, 2. Minus 2, 2 is going to be this vector here. And here we have it. Okay. Then let's have 4, 1. 4, 1. We can also define another vector. Let me think about it. Let it be, for example, this is 1. Actually, let's write this vector here for a moment. What did we write here? This was 1 minus 1. What was the other one? 3, 1. The other one, it was 4, 1. We have minus 2, 2. But we can also define, we can also have a vector which is something like minus 101 minus 98. Okay? And we can also have 2987 to 1002. Okay? So we have quite a few vectors. Let's keep those for a moment. Now, with these numbers and these vectors that we're trying to draw on the board, imagine for a moment that we want to have, this is 1, 2, 3, we can draw a circle with radius 1. Okay? Let me try to do something good, beautiful. So imagine for a moment that we have a circle of radius 1, and once we have this on the board, we want to define a unit vector. A unit vector is a vector such that the magnitude of vector v is equal to 1. Okay? So this is the definition of a unit vector. So, for example, which vector has unit length 1? So based on this here, as examples, we can have the following. 1, 0, this is unit vector. 0, 0, minus 1. This is also a unit vector. Now, if you have any question, why is it a unit vector? How can we make sure it is a unit vector? What we do is that we take the inner product of this second vector with itself. What would be the inner product of this one with itself? Let's do it right away. We take the transpose is 0, 0, minus 1, right? We multiply with 0, 0, minus 1, because we always take the transpose first. And then we do 0 times 0, 0, plus 0 times 0, plus 1. Square root of 1 is equal to 1. Good. So the second one is also a unit vector. Also, we can have 1 over square root of 2 minus 1 over square root of 2. Okay, this is also a unit vector. We can check if this is true. You can do this on your own. But now, so we define the unit vector. Now, what we need to do, we need this unit vector because very soon, when you go into more advanced classes, like in the third year, you might be, for example, in machine learning, often you want the computer to compare or to calculate the similarity between two data sets, okay? Or you want to do pattern recognition, you want to do iris recognition, you want to do, how can I say, something like car recognition, or to distinguish between different objects. For this, what computers do is that you have to write a nice algorithm and to generate a feature vector. So the keyword which you are going to need in short amount of time, this is a keyword. You need to generate a feature vector, okay? Last time we said that a feature vector of a tree can be different from a feature vector of a car, okay? And then what computers do, which don't see shapes, don't see contours, but they see numbers thrown out there, okay? Which to a human eye, they seem random. But what computers do is that they extract feature vectors and then they try to compare these feature vectors. And often the magnitude is not important, okay? And for example, you could have a feature vector of a tree, which could be this. It could have a feature vector of a tree, which would be this. It's hard to compare those because the magnitude of this vector is, what is the magnitude of this vector? 1 minus 1. It's 1.4, the square root of 2, right? So the magnitude of 1 minus 1 is 1. Let's do the inner product with itself. So here 1 minus 1. You multiply with 1 minus 1, and we get, the magnitude is always the square root of this, right? So you get square root of 2. But anyway, it's 1.4. So the magnitude of this vector is 10 to the power 0. The magnitude of the second vector is also 10 to the power 0. It's something like a number from 1 to 5. Okay, that's what we call 10 to the power 0. And this feature vector, let me erase this word for a moment. And it goes on like this. Here, we're talking about a vector which is 10 to the power 2. And here, we have a vector which has a magnitude of something like 4 times 10 to the power 3. So, we have a range of up to 3 orders of magnitude higher, but we want to compare the similarity between this and this. What do we do for this? We normalize all of these vectors. Okay? We do normalization. Normalization is defining a unit vector along the direction of a vector. Okay? Actually, if you check, let me see. 1 minus 1. I think this vector is complete negative of this one. Okay, if you normalize them, this has an angle of so this minus 101 minus 98. It's somewhere here. Okay, but this 3000 with 1000 is an angle of 45 degrees this way, and this is 45 degrees here. So we can predict where they are going to be. But now let's see what is this normalization, which you should take good note and write down on your notebooks, because it will be determining a vector of length 1 for this vector is going to be here. For this vector, which is 1 minus 1, it's here. So it's a vector which preserves the direction, but the magnitude is limited to 1. And then we have it here, here. For any other vector that extends like this, it's going to be this vector. And then when we compare these feature vectors, we compare the angle between any two. So if two angles are, the magnitude can be a few orders higher, but once you normalize them, once you bring them with a magnitude of 1, if the angle is very small, you could see that they are similar, these vectors, okay? Because since we don't have infinite precision, it's very hard for two different data sets that are similar to get an angle of 0. Always there is some error, there is some epsilons. Machines, computers, they have some epsilons which can never converge to 0, but any number which is 10 to the power minus 15, 10 to the power minus 14 is a 0, okay? Is the epsilon or the smallest possible calculatable or that can be computable numbers, or difference in numbers, or the errors in calculating a large number. This is what we call an epsilon, which I'm pretty sure that you are learning it in the best way possible in calculus. So, so we understand what these normalization of these vectors are. And for example, how do we do this normalization? Let's come now to the definition. The normalization, it is defined or maybe normalization is obtaining a unit vector. Let me write a unit vector. We denote it like this because it has a magnitude of 1. And along the v, or let's write it like this. The unit vector corresponding to vector v is going to be equal to vector v divided by the magnitude of vector v. Okay, so this is the definition. And now let's find, for example, the unit vector of the vector 1 minus 1, which we have here on the board. This is our vector v, and let's say this unit vector here along this v is going to be equal to 1 minus 1 divided by, what is the magnitude here? I think we did it.
1.
No, it's square root of 2, it's not 1. So, Drini, where Drini here, is it clear why the magnitude is square root of 2?
It's 1 divided by square root of 2, and minus 1 divided by square root of 2.
Okay, that's true. Because actually we can write it also like this. Thank you, Drini. This is 1 minus 1. So we know that when we multiply a matrix by a constant number, this constant number multiplies each one of the elements one by one. So this is going to be, as Drini said, 1 divided by the square root of 2 minus 1 divided by the square root of 2. Fine, we found this unit vector. Let's pick up another one, this 4, 1, for example. 4, 1. The unit vector with length 1, this is what we mean, along the v, is going to be, let's find out what is the magnitude of 4, 1. I want Andre to follow me here. So Andre, what could be the magnitude of 4, 1? write it like this. Wait a second. Let me write like the magnitude of V is equal to the square root of V. Yes, you can continue, sorry. Andre, yes, help me here. And this is equal to the, or I can do it, you can check my mistakes.
15.
So it's 15. Let's follow this carefully. 4, 1. This is a transpose, right? We multiply with 4, 1 again. Because we're trying to find the magnitude, so it's square root and so on. So this is equal to the square root of 4 times 4, 16, 17. Square root of 17. That's true. Okay, we got it. This is square root of 17. This means that this is 1 over the square root of this prime number times 4, 1. And as we said, any constant multiplies each element 1 by 1. And the unit vector along this is going to be 4 divided by the square root of 17. And 1 divided by the square root of 17. Okay? Now, as we're working with the matrices, we can remind each other once in a while that even we always have to be careful to remember what operations can be done with a matrix. Because if you go, when you go to the, let's say to third year, or when you go to the master studies, you're going to see that matrices, they're used a lot for a lot of complex operations, where one of the most interesting one can be, for example, for self-driving cars. This is a classic example, that the car has a very nice camera, and the camera has to do some analysis, and sometimes you have to do deep learning, and when you do deep learning, it has a very high computational power. You need to apply certain, you have to multiply a huge matrix by small matrices. These small matrices, they can be of size 3 by 3. So let's say here we have a huge matrix, and then this is separated in rows and columns, okay? And then what happens is that you have to multiply the whole matrix by defining certain regions. You multiply element-wise a 3 by 3 matrix with which is the output. It's an input, and it multiplies different regions which are all 3 by 3. And you try to extract specific features. Then you can follow this operation by another matrix which can be 5 by 5, and so on. And often, the outputs of these multiplications or convolutions, this is how, now, I want to mention this keyword convolution now, because you are doing the linear algebra, and also for the sake of the great use of machine learning. We could even call this course of linear algebra such as linear algebra for machine learning. Okay, because you have to know where you're going to use this, and they do find great use in these applications that we're just talking now. So you can keep note, this can be considered like a correlation. This is one way how matrix manipulation with another small matrix or with another kernel, this is a key word that you're going to hear this a lot. When we do this, you should always be careful, because sometimes some multiplications that are not defined at all, okay? You feed this into a programming language, but it won't work because it's simply the dimensions don't match. Or sometimes you're going to see that often some operations which are applied in machine learning, you don't always need to have, you know, that when we add two matrices, we can add a 5 by 5 to a 5 by 5 matrix, or a 7 by 3 to another matrix which is 7 by 3. But sometimes you need to concatenate different matrices. In this case, just the matching of one dimension is enough. Okay? So this means that you can merge together a 7 by 2 matrix with a 7 by 5 matrix, and you preserve, you keep equal only one dimension. Okay? So these are some small tricks, not tricks, but something that you already know. But you should not go to apply some complex algorithm and forget this nice and important essential properties of matrix operations. So keep in mind that how specific multiplications or specific addition subtractions, how special conditions have to be fulfilled. Now, we left the discussion with when we were talking about the normalization. Fine, we did this. It looks like we have identified a couple of vectors here, and as we said, once all of them have a magnitude of around 1, we start to look for similarity, which is described by the angle between any two vectors. This is good. Now, one thing that I can add here is also the fact that there is some similarity between the matrices and vectors and complex numbers. Okay. Now, complex numbers, we can, just as a reminder, I'm sure that you already know the general definition of a complex number, which is, for example, that the square root of -1 is equal to I, okay? And I squared is equal to -1. And if we have a complex number that, wait a second, maybe I can use this a little more efficiently, which would be, so I want, Aned, can you help me here? Can you give me a complex number? Tell me one number.
-2 square root.
Square root of -2, that's perfect, okay. Z is square root of -2, which is going to be equal to square root of -1 times square root of 2, which is equal to square root of 2i, okay? Square root of 2i, it's it has only the imaginary part. The imaginary part, this is 1, this is 1, this is 2, this is 2, and square root of 2, it appears, so this is the imaginary part of the complex number set, this is the real part of the complex number set, and the magnitude of square root 2 is somewhat like 1.4, okay? So it's this point, okay? So that's one number. Another number that I could provide is also allow me to give this 2 plus I. So this is Z1, it's here. We have another complex number Z2, which can be 2 plus I. 2 plus I, with the real part of this number is 2, I, we find it here. So here we have a vector, which is Z2. And in a complex number coordinate system, which is similar to the Cartesian system, this is how we show them. Now, why did we mention this? Is that last week, when we started the discussion of the possible operations that we do with a matrix, we said that we can add them, we can subtract them, we can also multiply them, but the division is never defined. Okay, so we can never divide a number with a matrix. This is simply not defined. We cannot divide two matrices also. Similarly, we cannot divide by a complex number. Okay, so this I want to mention this one because when in a few weeks, when we're going to start to discuss about the eigenvalues, okay, eigenvalues. And eigenvalues, sometimes they can be numbers, they can be real numbers, okay, they can be real numbers. They can be also complex numbers. So complex number space is this C with double curvatures. So when you discuss about eigenvalues, we're going to see that eigenvalues, they belong to a matrix. So what a matrix can do to a system, once we operate with a matrix, the same thing can be done by its eigenvalue. So for the sake of this equivalency, which I'll try to make it clear in a few weeks, I just want to remind you also about this one, that so we're talking about the equivalency between vector V and complex number Z, okay? Complex numbers, often we denote that with Z. So for a moment, I can ask you this, what is 2 divided by 2 plus I? This is a division, but it is simply not defined, because what we do in this case, we do 2 plus I, we multiply by 1, right? But this one, we can write this with 2 minus I, and 2 minus I. So this is the complex conjugate. Complex conjugate of Z2, we show this with the star, is equal to 2 minus I, and this is called complex conjugate sorry. And now, what would be the answer if we multiply with these complex numbers? Who can help me here? We have Ernest here. Ernest, how should what is this equal to?
It's 4 minus I, 4 minus 2I,
divided by
4 plus I square. 4 minus
4 minus 1, that makes 3.
Am I correct here?
I think no, because minus minus is plus.
Yes. Which makes this 4 over 5 minus 2 over 5 times I, okay? So, we said that this division is not defined with complex numbers. Also, division by matrix is not defined. Division by vector is not defined. Then, we can also say that the complex numbers, they also have a magnitude. And this magnitude of complex numbers is defined as the length of this vector, the same way that we defined the magnitude before. And the magnitude of a complex number is also defined as the Z conjugate, complex conjugate, multiplied by Z square root, okay? This is the magnitude of a complex number. So it's almost very similar to the vector magnitude. So for this Z, for example, which is 2 plus I, what is the magnitude of 2 plus I? Is the length of this vector, right? Using the Pythagorean theorem, we do 2 squared, this side squared, plus this side squared, we get the hypotenuse squared, right? Which means that this is something like square root of 5. Then, let's see what we get here. I guess you could agree that complex conjugate of Z, this is 2 minus I times 2 plus I, and we get square root of 5. Why do we get that? 2 times 2 is 4, plus 2I, minus 2I, minus I squared. Okay, they cancel out like this, and we get the same number. How did we find the magnitude of vectors? We did vector transpose times a vector square root, right? So this was still the magnitude. Now, there is a little more advanced branch of mathematics, which you are not required to learn to understand it right now, but there are also vectors which include inside also complex values. For example, in analysis of quantum systems, often the probability of a specific state is equal to the V transpose times V. But this V can include also complex numbers, and in this higher level of mathematics, you do both at the same time. You take the transpose and also the complex conjugate. If all the numbers are real numbers, complex conjugate of real numbers is equal to that one at the same time, right? So nothing changes. But in principle, it might happen that you might open a book, and you might be surprised, and maybe it's not the book that maybe you pick the wrong book at the library, because you don't often see this unless you go and study for quantum computing, and then you need to understand this quantum nature of how we denote the probability state of some specific condition. Then you might end up into seeing these vectors having also complex values, and you do these two operations at the same time simultaneously, and things will be fine from there. But what I cared for now, it was just this idea that vectors and complex numbers, they are equivalent with respect to some properties. This is not equal, this is equivalent sign. Okay, so these were some, let me see, some important aspects that we wanted to discuss. And then from here, let me see, we discussed the normalization, the unit vectors, everything is fine. Okay. Now, we said at the beginning of today's course, we said that what was the union of, well, we can write it, actually, we argued that a line, L1, it can be described as C times T1, okay? So this was a line, okay? Well, I think we argued on this one, most of you agreed, and I can ask one question. Does this line pass through the origin? What do you think, Enrique Kumi?
Yes, I said that the line passes through the origin.
That's correct. Okay, so this is a line that passes through the origin because this C, it includes the zero, okay? What about, so this means that if T1 is a vector that looks like this is the vector T1, this can define a lot of points that in the end, you can just draw a straight line and say that this is the line passing through the origin. Now, we can have another origin included, or how can I write this? We can say 0, 0 is a member of L1. This is how I can write it. So 0, 0 is included in L1. Now we can have another line L2, which can be defined as P plus C times T1. What is this? This P, in case P is non-zero vector, this means that we have shifted the whole line to some value P. So this vector P can be here, okay? Which means that any point afterwards is going to pass around here, and in this case, 0, 0 is not a member of L2. Then we can move further and we can define the equation of a plane. The equation of a plane, it can be written as, let's write this one as P1. P1 is equal to C1 T1, where T1 is a vector, plus C2 T2. T2 is also a vector. So this is a plane, okay? And the question is, again, will this plane pass through the origin? What do you think?
Yes.
Yes.
It does, because C1 and C2, we are not excluding the option of C1 and C2 being zero at the same time. So it passes through the origin. So if you have an XYZ plane like this, we can have a plane which can pass like this and at a specific angle, but it will include this important point. Also, we can have a plane P2, which can be defined as this is plane P2. We can write this as vector P plus C1 T1 plus C2 T2. This is again a plane, but this does not pass through the origin. Okay, so and I think the moment we write a vector P here, we are excluding the case when P is equal to 0. Or we can also add that if P is 0, this will include the origin, or it will pass through the 0, 0, 0 point. Okay, now let's see an example. So let's try to find the vector equation line that goes through these 2 points. Okay, how we can determine the equation of the line. Now, what is, if we want to determine a line, what is the most important parameter? One of the most important parameters would be the direction. Okay, so now let's try to visualize as best as we can. So here we have a point -1, 1, or -1, 1. It's a point that looks like this, because x is -1, y is 1, and we have 3, 2, 1, 2, 3, 2. Here we are. So we have this other point. Now we are asked about the equation of a point, a line that passes around here. Now, how can we find a vector that has this direction? Any idea?
Is it the difference between those vectors?
That's a good.
The difference.
The difference. That's true. So let's assume this is point P1 and this is point P2. But at the same time, these are vectors. So this one, any vector that has this direction, it's either P1 minus P2 or P2 minus P1. It's fine. Which in this case, this would be, for example, we can pick up this 3, 2 minus 1, 1. Okay, which makes this 4, 1. Okay, so it looks like a vector or a line which passes through these 2 points, and we tried to draw this one to scale as much as possible, which means that this is 1 unit, 1 unit, 3 units. Fair enough, it doesn't look that bad. And we got an answer 4, 1. What does 4, 1 mean? 4, 1, this is 1, 2, 3. 4, 1 is somewhere here, and 1 is somewhere here. So it looks like we are getting a line which looks more or less like this. It looks good. So most probably we were correct when we determined this slope, which has to be parallel to this. So we found the vector. And now it looks like this line, we can write this line as c times 4, 1. Okay. If you go back to the beginning of today's class, we said that this is a line, right? Which you just multiply and it goes back and forth. But now it looks like our line does not pass through the origin. This does pass through the origin, which means that we have not found the final answer. To find the correct answer, we need to do something like this. We have to do c times this plus some values. I don't know. Let's write some a, b. Okay. Some random values, because we need to write an expression like this. The moment that we exclude the origin from being part of the line, we need to add this, and this then would be equal to what? This is going to be equal to either this point or this point, right? So we want to force this line to pass at least to these 2 points which are given. And in fact, since this is a straight line, we can even determine a lot of points, at least in between. I think we can do it. We are at that skill. But let's assume that we want this to be equal. So this is a question mark. This can be both -1, 1. Okay, so we can construct one equation just by writing this like this, or 3, 2. Okay, so we can, it can be any one of these. And what else can we say? And what we can do, we can also have any one of these points themselves as references. So line L1, this can be -1, 1 plus C, this is any constant C, times 4, 1. Okay, so this is a possible answer. Now, I can also ask you this. What is the slope, since we're considering or analyzing the geometric understanding of space? What could be the slope of this line? Slope është pjerësia.
Coefficient Condor.
Drejt, or how can we define it? Arione, can you answer this? Ariel Tobli? What is the slope? So we have a line, so slope is pjerësia. This is a small slope, okay? This is a higher slope, we are increasing the slope, and this slope is infinity. If the angle is 90 degrees, this is infinity. So,
Tangenti I këndit që formon.
exactly, that's true. This is the tangent of the angle theta here. And what is the tangent? It's 1/4, okay? Because this point, the tangent of this angle is always the opposite side divided by the adjacent side. So tangent, tangente që u përmendet ju, tangent is equal to opposite side divided by adjacent side of this angle. So since we're looking for this angle, the opposite side is 1 divided by 4 units which are on this side. So this is an angle theta which is smaller than 45 degrees. Okay? So we can extract this much information. Now, we can also ask the following question, which would be, if, so let's say this line of interest is going somewhere like this, okay, so it will extend, okay, fine, it will go like this. What if somewhere here, imagine you put x10, 10d. So most probably this line at one time it will intersect this x is equal to 10 line. So look at this expression and find d. Okay? So this is like an exercise from you, and next time I want an answer from Erwin. Okay, Erwin, next time you have to solve, because you are the next in line. I wanted to solve a couple of examples using the planes, but probably I don't have all the possible time. But at least what we covered so far. Do you have any question? Is there anything not clear? In fact, the time is very, so actually this difficult question I want to ask Eugen. Eugen, the first one, wait. Eugen coaching. Is there anything not clear? Okay, thanks. Or Rudy, thanks. So if everything is fine, we can close this class, because probably some of you might have another class following. But wait a second. Yeah.
Professor, can I make a question?
Sure, of course.
Which of the books is the first book that we should for this class?
Is Anthony and Harry. These are the authors.
Okay, thanks.
You're welcome. Any other question?
Profesor, te kush kapitulli gjem të mësimin?
Me shumë si është dyshi.
Kapitulli 2, ëh? Okej.
Në rregull. Ndërkohë, atëherë këtë sesionin po e mbyllim në avash avash, dhe do i thoj diçka që